Hello, this is lecture 8 of mlcourse.ai, and today we're going to cover a very popular optimization technique called Stochastic Gradient Descent. So it's really very important because most of neural networks are still trained with this algorithm. So though it originated really very long ago, but still it's useful for training networks or different models on really large datasets. So we're covering here SGD. So it's simply called SGD. S stands for stochastic, and GD stay for probably the simplest optimization method that we covered, gradient descent. And let's quickly discuss how typical gradient descent, which is usually called batch gradient descent, how it can be generalized to work efficiently on large datasets. Let's again go back to our simple task of paired regression. So we'll have one feature y, and we are going to predict it with just one feature x. Let's suppose that these features correlate really highly, and we are going to build a linear function, a very easy one, just for our toy example. So we are building a linear function of our prediction y hat is going to be w0 plus w1 multiplied by x. Okay, so or it's going to be w transposed multiplied by x. In a matrix notation, we'll simply write that y hat equals x multiplied by vector w. And here by x will mean a matrix of dimensions L, the number of instances in our case, by d plus 1. So it's in general case, in our case d will be equal to just 1, the number of features or predictors that we're going to use. So this will be just a matrix L by 2, and we'll have a column of all ones. This will allow us to write this equation in a very nice form. And so here we'll have x1 and so on till xl. Okay, and vector w, so this is matrix x, and vector w will be a vector with w0 and w1. Okay, so just quickly recapping. So we'll be using mean squared error to actually find these coefficients. Remember, their meaning is pretty simple. So w0 will be here, this distance from the origin to the intersection with axis y, and w1 will stand for tangent of this angle. So we've got a line, and we've got some angle alpha here. So actually w1 will correspond to the tangent of this alpha. Okay, so to actually find a nice prediction here, so nice values of w0 and w1, we'll be minimizing mean squared error. So the sum over all our L examples from 1 to L, the difference between the actual value yi minus the prediction yi hat squared. And it's a mean squared error, so we'll divide by L. Okay, and in our simple case, this is going to be 1 over L, and we'll have this difference here, yi minus w0 minus w1 multiplied by xy, and all of these squared. Okay, so this was really simple, so we are just recapping. But think, what if L is very, very large? So the problem will be that we need to calculate this MSE, and so we've got here a sum over all our instances. So if L is much bigger than 1, so a mathematician will write much bigger than 1, I'm going to write something like much bigger than 10 to the power of 5, 100,000. So if we've got millions and billions of samples, so this is not going to be really nice. So calculating MSE will involve calculating this large sum. But let's go to gradient descent. So again, quickly recapping the idea of gradient descent. We'll be calculating the gradient of this function. So a gradient is actually a vector of partial derivatives. So a gradient of MSE is going to be just a two-dimensional vector. So its first component will be partial derivative with respect to W0. And the second component is going to be the partial derivative of MSE with respect to W1. And so now we'll see that we've got problems, computational problems, that with these partial derivatives we are still left with this huge sum, E from 1 to L. Okay, let's carefully calculate these partial derivatives, and we'll see how we can alleviate this problem with all these large sums. Okay, so again, our MSE. And let's carefully calculate its derivatives. So in our simple case, we'll have only two coefficients that we're tuning, W0 and W1. So the partial derivative of MSE with respect to W0, so we need to differentiate with respect to W0, so we'll have all this big sum again, so it will remain. And we are differentiating this inner expression, so we'll have 2 as a multiplier, 2 over L, so this constant 1 over L remains the same. And here we just treat this function as just some expression squared, so we are differentiating it, and we've got the very same expression. And now the derivative of this expression with respect to W0, we've got minus here, so we'll have minus 1 as a multiplier. Okay, and the very same derivative, but with respect to W1, so we'll have again this big sum. This expression is the same. But now, as we have a derivative with respect to W1, we'll have a multiplier minus xy. So this is actually the only difference. And again, if we have a really large dataset, we'll have these big sums actually in formulas for partial derivatives. So now let's take a look at the gradient descent. So if we draw a picture of our loss function in the weights space, so if it's going to be W0 and this axis is W1, then our loss function is a quadratic function of these weights. So if we draw its counterplots, so this ellipse is going to be a curve where all the values of the function MSE are equal and maybe some large value. So now another ellipse where function values, this MSE values are lower, then again the same values on this curve, but they are lower, and then we have some global minimum here. So this is going to be the minimum of MSE that we are looking for. And gradient descent will actually initialize with some random values of W0 and W1. So we'll start somewhere from here. So these are going to be W0 and W1 at step 0, so our initialization. And then we'll calculate gradient. So it's going to be a vector which is perpendicular to these counter curves. And we'll make a small step towards anti-gradient. So we'll make a small move here. And then again we'll be recalculating gradient, again we'll go towards anti-gradient. So because gradient is actually a direction where the function grows at the highest rate. So anti-gradient is going to be the opposite direction, where the function is decreasing at the highest possible rate. So actually that's the idea of gradient descent. To minimize the function as quickly as possible, we need to go according to the direction of the anti-gradient. And so here slowly and slowly we'll be reaching this minimum. So if we write a formula for gradient descent, so we'll have some vector W at step t+1. So it's going to be calculated with the previous value of this vector W at step t. So we are going to make a small step towards the gradient of our function that we are minimizing. In our case, it's MSE. The gradient estimated at point WT. And we make some step proportional to this anti-gradient. So we need to calculate the gradient, then anti-gradient, so the different, the opposite direction, and then we make some step in this direction. So this step is regulated by this coefficient eta. So there is much more theory on how you tune this eta. So the simplest way will be to make eta proportional to 1 over t. So with our steps of gradient descent, this coefficient is going to decrease. That will mean that at first we'll be doing large steps, and then when we've reached the region of low values of our function, then we'll be doing smaller steps to more accurately find this minimum. Well, so actually neural networks were known for quite a while. So let's say in the beginning of the 12th century, in 1950s, we already knew a lot about neural networks, but there were some problems with actually making them work. And in particular, there were problems of minimizing all these billions of weights. And so actually a lot of qualitative progress in neural networks was done in optimization. So how you actually make all of this work, all these policies of decreasing all these learning rates, sorry. This is nicely described in the book Deep Learning by Goodfellow, Deep Learning book. So here they have a nice introduction to mathematics, linear algebra, probability, numerical computation, and then machine learning basics. So this part 1, chapter 4, so this covers numerical computation. So if you're interested, all these small improvements in optimization techniques, they eventually lead to actually training these huge neural networks. So very often theoreticians underestimate this importance of actually optimization and say that, well, neural networks were known for quite a while in the beginning of the 20th century, but still indeed, it was really very, very important to make it work, and lots of our knowledge came from the field of optimization. Okay, so we've got a problem that even estimating the gradient, so calculating these partial derivatives, invokes this huge sum over all of our instances. So typically gradient descent needs some dozens of thousands iteration to reach this minimum. And you see at each point, so let's say somewhere here we've got point W at step t, W0, t, and W1 at step t. And so we're actually estimating gradient here, and you see it requires a lot of computation just to estimate gradient. So estimating the gradient is analogous to actually orientating where we need to go to decrease our function. And so even doing so, even computing gradient, you see, is pretty computationally intensive. So stochastic gradient descent will be very informally. It's just throwing away all this huge sum. So it's a very, very informal introduction to stochastic gradient descent. So we are just getting rid of this big sum, and therefore we lose something, of course. So we don't know the exact gradient anymore, but we'll be updating weights, seeing new instances. So graphically this will mean, okay, I'll draw it in blue. So stochastic gradient descent will correspond to throwing away this big sum. And in this picture, it will mean that we don't know exact gradient. So let's suppose we start with some new random point. So we're not calculating gradient, but we do some small weight updates. So graphically it will look like this. So we'll be doing much more iterations. But these iterations will be much quicker to compute. And then finally we'll reach the very same minimum. And it's theoretically it's the most important part about stochastic gradient descent, that eventually it's going to reach the very same local or global optimum as gradient descent, normal, which is called batch gradient descent. So here is a stochastic version. And the previous one was normal gradient descent. Which is called batch gradient descent. Okay, now let's see how it works actually in practice. So let's suppose that we've got a really large data set. So now closer to real computations. So we'll have, let's suppose that we'll have a big disk, HDD, maybe it's 1 terabyte. And here we store our training data. So actually it will correspond to these pairs X and Y. So now we're going closer to online learning. So stochastic gradient descent is an optimization procedure that makes online learning actually work. So this is has nothing to do with MOOCs, massive open online courses. So online learning is actually a machine learning term that stands for training a model without actually loading all this data into memory. So suppose this is our training data is 1 terabyte, but we've got only small RAM. Let's say our RAM is just 8 gigabytes. Okay, not just 8 gigabytes. Actually, 10 years ago it was pretty nice to have 8 gigabytes of memory, but still, let's suppose our RAM is very small and we can't load all this training data to our memory. So what we're going to do with SGD approach, we are going to read instances one by one into our memory. So we take one instance from this HDD, so from our training data. So this is actually a pair, let's say x1, y1. We initialized our weights, so vector w at step 0. We just initialized it with some random values. And now when we read this pair, this training instance x1, y1, we just do an update in the very same way as we did it with gradient descent. Yep, so we've written this formula, so we had derivatives. Let's just combine all of it in one formula. So we'll have for w0 at step 1. So we'll calculate it through w0 at point 0, at step 0. So we need to move to the direction of anti-gradient. So we'll have -1 eta, and then anti-gradient. So remember, we had 1 over L here, actually 2 over L here. Then this big sum that we are now going to skip, and yi minus w0 minus w1 xy. And then we also had -1 here, so this minus becomes plus. So what I'm writing here is actually corresponds to a very simple formula for weight updates in the gradient descent that we just made, that we just covered. So vector w at step t plus 1 is calculated via the very same thing at step t minus eta and gradient of the function that we're minimizing, L, at step t. This is just the same, but we don't calculate the full gradient here, so we don't write this big sum here. We only update the weights with respect to this first pair x1, y1. Okay, so in our case, this index I is going to be just 1. So we've read only the first pair. Okay, so actually these indices 1 correspond to just the first instance in our training set, x1, y1. Okay, so I'll color it green here as well. This is x1, y1. Okay, and to be precise, so here we've updated it with the initial values of our weights. So this was at step 0. Okay, and the same with the second weight. So w1 at step 1 will be calculated in the very same way, but the derivative was a bit different. So here we had eta 2 over L, the very same thing, but now also in the derivative with respect to w1 we had also x. Okay, so here we have a multiplier x1 at step 0. Okay, and so actually we've performed just a simple weight update only by reading the very first example. Okay, and then we are reading the next example, let it be blue. So the next training instance is a pair x2, y2, and we perform the next update. So we'll have w0 at step 2, and so again it will be calculated in the very same way through w0 at point 1. And so here plus eta, blah blah blah. And the same for w1. Okay, and so this is the original version of stochastic gradient descent. So when we calculate gradient strictly, so this is called batch gradient descent. When we read instances one by one, this is stochastic gradient descent, and a perfect mixture is something in between. And so the most popular way is actually a MiniBatch gradient descent. So currently now, if you say stochastic gradient descent or SGD, actually by default you would mean MiniBatch version. So a MiniBatch gradient descent will be almost the same, but we are going to read a small, so it's called a mini batch of examples. So it's going to have size k. So this k, something like 32 or let's say 128 or 512. So typically some power of 2. So we'll be reading a portion of training instances, and we'll update the weights with all of these training instances. So a mini batch version will leave the sum. Okay, so let this magenta color correspond to mini batch version. So in a mini batch approach, we'll still have this sum. Okay, let me start from scratch. So a mini batch version will still leave this sum, but it will be a sum not over all of our instances, which if we have really billions of instances, it's not going to be efficient. But in mini batch version, we'll update our weights, let's say wj. So it will be calculated with wj at step t, but now we'll leave this sum, but now it will be calculated with a mini batch of data, if from 1 to k. And so k is typically something like 32, 64, some powers of 2's, maybe up to 124. And so here the same formula for derivative, but this is going to be a mini batch version of gradient descent. So this is going to be mini batch gradient descent. Again, we don't know gradient precisely, but we are only approximating it with a mini batch. Okay, and again, returning to this picture, so we are having a big disk, HDD, one terabyte of data, and in our RAM, we only need to store actually only this vector of W's. Okay, so we are reading our data batch after batch. So first mini batch with updated weights. So first we have W0 at step 0, then we'll have the very same W but at step 1. So not the same, but we've updated it with the first mini batch of data. Then we take second mini batch, read it into memory, and so we'll have W at step 2, and so on. And so until we've covered all of our data, so when we've finished covering all the training set, so we've split it into several, maybe hundreds of thousands of mini batches, and now we are done. So this will be called one epoch. So one epoch is running this procedure through all of our data set. And so typically to make this procedure converge, we'll need more than one epoch. So maybe 5 till 10 epochs to actually make this procedure converge. So in a nutshell, this is the idea of stochastic gradient descent. And for now, we've covered it for a simple case of regression. Let's quickly discuss what will change if we switch to classification and logistic regression. So you see, gradient descent is a very general optimization procedure. So if you know how to calculate derivatives and so gradients, so then you'll be able to minimize almost any function. So it can be applied to regression, classification, to ranking. So whenever you can calculate the gradient of your loss function, then you can apply gradient descent. So next time we'll cover Vopel-Webbit. So it's in a nutshell, it's a library which implements the idea of stochastic gradient descent very efficiently. Sorry, Vopel, yeah, a bit strange name, Vopel-Webbit. It's something about a rabbit and a girl with not imperfect pronunciation, so she calls this rabbit Webbit. Then some Vopel also stands for some variant of Varpal. Okay, so you can read about this name. It's indeed strange, but the idea is that it's a very efficient implementation of the very same idea for different models, for classification, for regression. So even for simple neural nets, you can apply this idea. But we'll cover Vopel-Webbit next time. It also applies some really smart techniques to work with large feature dimensions. In sklearn, this idea is implemented with SGD classifier or correspondingly regressor. SGD classifier or SGD regressor from the very same module sklearn linear models. Okay, so let's discuss what will change if we do classification with logistic regression, and then we'll implement a simple regressor that is trained in a stochastic version. Okay, so if we now solve a binary classification task with logistic regression, so I'll quickly cover what we did in topic 4. So we'll be building some hyperplane, which is going to separate pluses from minuses, maybe not perfectly, maybe some pluses here, some minuses here. And this is going to be our feature space, x1, then it's a multi-dimensional picture, let's pretend it to be, then xd, and so on, d minus 1, xd. Okay, and so we are solving a binary classification task. So if you go to topic 4 in our course, we are covering there in detail how you actually come up to some function, then which, if minimized, will lead to a nice decision boundary like this, a hyperplane. So we cover there logistic loss, which is 1 over L, again, big sum of E from 1 to L, so over all of our training instances, and then logarithm 1 plus E to the minus margin, minus yi, w transposed xy. Okay, so this was our result from topic 4. So if you go to mlcourse.ai, yeah, strange. Maybe it's popular, maybe that's why we need some time to wait for it to load. Okay, so topic 4, linear classification and regression. So we cover logistic regression here. Okay, let's wait. And then there were some nice theoretical ideas of maximal likelihood estimation, which led to minimizing a really very specific function of training data and weights W. Okay, maybe some problems. What if we go to the main repo, mlcourse.ai? The very same material here is in README, so this is going to be part 2 of topic 4. Okay, so linear classification. So we're separating these dots in some high dimensional space. Okay, and so just go back to this material, and here we stopped at this logistic loss. And well, so please make sure you understand all of these steps, how we modeled probability of some label given data, and then applying max likelihood. And so we came to this formula for logistic loss. Let's see how we can modify it to train logistic regression in an SGD fashion. Okay, again the very same problem. So to calculate loss, we need to do these calculations with the whole of our data, and still the very same approach. So SGD will just get rid of all this big sum. So let's calculate partial derivative of our loss with respect to some weight Wj. So again, we'll have training data, we'll have a separate column of ones, and so this training data will be L by d+1 dimensions. So this is matrix X, we'll have a vector Y, and so vector W will be d+1 dimensional. So vector W, okay, we can write it horizontally because it's also d+1 dimensions. And let's take a look at the partial derivative with respect to some Wj. So somewhere here we'll have the jth component of this vector. Okay, so for now let's leave this big sum. So we are going to calculate this derivative. Yeah, sorry, one important notion that this formula is valid if our labels yi are either -1 or +1. So then we'll have such a formula. Another popular variant will be to make labels either 0 or +1, and then the formula will be a bit different. It will be a bit more complicated, so it will have two summands in it, not just one. So with these designations, the formula is a bit simpler, and we are going to take a look at this one. Okay, so if we are to calculate a derivative, we'll have 1 over L, then again this big sum. We need to differentiate this logarithm, so first we'll have this expression in denominator. Now we need to differentiate this expression with respect to Wj. So we'll have again the exponent, but now in nominator. And this expression W transposed xy, if we simplify it, so what actually this expression means? So this is W0 plus W1 xi, the first component. So now be careful here. We've got xy. Y here is the index of is a row index. Yep. So the index of our instance. And 1 here will be a feature index. Yep. So an index of a column. So then we'll have here somewhere wj multiplied by xy jth component, and then till wd xi component number d. Okay, and so if we calculate partial derivative with respect to wj, we'll have only one summand, one element with wj, and so if we calculate the derivative, we are left only here with minus yi. So if we are calculating derivative with respect to wj, so we'll have here xij. Okay, to simplify it a bit, here in this fraction we can multiply by e to the power of this thing without minus. Okay, so we'll have, maybe you can take a look at this expression and already see here sigmoid again. So this is actually, well, we again 1 over L and this big sum. And so here, if we simplify this thing, we'll have sigmoid of, well, we'll have 1 over 1 plus e to the power of this expression without a minus. So it's a sigmoid of minus yi w transposed xi. And this expression is still the same. Okay, so this is already a very convenient form, but typically they take this minus and modify sigmoid. So here we will use a very simple property of a sigmoid function, that sigmoid of minus z equals 1 minus sigmoid of z. And so now our expression is all this sum, 1 minus sigmoid of yi w transposed xy and yi xij. Okay, cool. So now we have an analytical expression for a partial derivative of logistic loss with respect to some weight wj. And now you see in SGD fashion we'll be just doing the very same weight updates, but without this big sum. So SGD for logistic regression will mean throwing away this big sum and making these weight updates as we discussed for regression, just in a similar fashion. We are going to read one example after another and modify the weights of our model according to this formula. Okay, so here I derived an expression for partial derivative with respect to some wj. Maybe I only need to say that if j is equal to 0, then we are left here with xy 0, which is in our designation just 1. So xy 0th element of our features is just 1, corresponding to this vector of all ones in our matrix X. Okay, so now you've got the idea of logistic regression trained on a very, very large dataset. We'll be doing very, very simple weight updates as in case of a simple regression, but the formula will be a bit different. So stochastic gradient descent with just a small modification with adding momentum is still a very, very popular optimization technique, and most of modern neural nets are still optimized by stochastic gradient descent with momentum. So I'm not going to cover momentum here. You can read it in this nice overview in the deep learning book. But the idea is that you see it's pretty simple and still very, very effective. Or I would better say efficient. Yep. So you see here we've covered how we can train a regressor in such a fashion, and then a classifier, logistic regression. And the very same idea holds for actually any function, as long as you can calculate its derivatives with respect to these weights, W's. Now let's go to a demo assignment. So if you go to Kaggle datasets, one moment. So on kaggle.com in datasets, you can find our course dataset, mlcourse. So here in datasets, mlcourse.ai, and here in kernels you can find, maybe if you sort by recently created, you can find a solution to a demo assignment that we're going to cover right now. So let's first take a look at the original version, not a solution. So to get the idea of stochastic gradient descent, let's just implement this simple online regressor. So we're going to create a class, SGDRegressor. So it's going to be inherited from sklearn-based estimator. So it will have methods fit and predict. So we'll be training a regressor in an SGD fashion. So we'll have some gradient step. So it's actually a learning rate. And we'll be training for some number of n epochs. So by default, this will be 3. So we'll make 3 passes over all our data set. And we will implement just an original version of stochastic gradient descent. So we'll be reading instances one by one. So in constructor of this class, we'll have MSE. So we'll keep track of MSE by iterations, by all of steps, and the weights themselves. So we'll have to implement fit and predict methods. So the fit method will take our training data, matrix X and vector Y. So these are NumPy arrays. So we'll have to add a column of ones to this matrix X. We'll initialize weights with zeros, and we'll do n epochs iterations of weight updates. So now we'll, what's also required? We'll store the current minimal mean squared error in a special variable. And then the predict method will take a matrix X. It will add a column of ones to it, and will multiply by weights, and this will be our prediction. Okay, and we are going to test it with simple data, heights and weights. Okay, let's go to solution. So this is a demo version, so that's why the solution is shared. You can fork this notebook. And now it's basically a Jupyter notebook, but you can play around, you can modify it. So let's run this notebook and see how actually easily this idea is implemented. And the very same code can run on with some efficiency modifications. It can run on really large data sets. Okay, so let's maybe first take a look at our data. So these are demographic data, weights and heights of several thousands people. Let's take a look exactly. The shape of our data frame is 25,000. Okay, and so here is a scatter plot. So yeah, indeed, weights and heights are very highly correlated. And yeah, just in this assignment, we're going to predict height in inches as a linear function of weight, which is in pounds. Okay, just as an example of such a regression problem, we're not actually going to be interested in that, just an illustration. Okay, so we'll split our data. 70% will go for training part, and then 30% into test part. And we're going to scale our data. So with standard scaler, we apply fit transform to xtrain, and then we transform our validation set. Okay, and let's go into this SGDRegressor. So this is the constructor. So it will be called when we create an instance of this class, SGDRegressor. And yeah, let's start with the first line. Yeah, so the class is inherited from sklearn's base estimator. So here it is, from sklearn base, we import base estimator. And this will oblige us to implement methods fit and predict. So here in constructor we'll have eta, our learning rate. By default it's equal to 10 to the power of -3. And we'll initialize an epochs, so the number of epochs that we're going to perform on our training data. So you see with saved eta, we saved an epochs, and we also create here lists to store MSE by iteration and weights. This underscore typically means that we are going to treat it as a private attribute. So in Python we don't have private or public methods or attributes, so that's why we'll just pretend that it's private by putting an underscore here. Okay, and let's just see how easily the formulas that we covered 10 minutes ago are implemented in code. Okay, so first here we'll add a column of ones to the left from the original matrix X. So here we add a column of ones to the left from original X. And here we initialize weights just with zeros. Okay, and we need to pass the number of features. So this X shape and the element with index 1 will correspond to the number of features. So actually this is d plus 1 dimensional. Oops, sorry. So it's d plus 1 dimensional in general case, but in our case we do just paired regression. Let's again take a look. So this data demo is 25,000 by 3. Let's take a look at this data frame. Okay, we've got index here, so we'd better read this data by passing index here. Okay, but actually we've got only one feature that we're using for prediction, so d here is equal to 1. And we're going to predict height with this feature. Okay, so in our case, x now will be two-dimensional, so d is equal to 1. So actually this will be a two-dimensional vector. Okay, now we'll do this n epochs iterations over the whole dataset, and we'll be reading instances one by one. So that's why we'll have another for loop with e iterating from 0 to you see the shape of this matrix X. And now we're actually performing weight updates. So we'll treat the 0th element separately. Yep. So our formula, you see, multiplying by this eta, and then this difference yi minus w transposed xy. Okay, and then we'll have another loop over all the remaining features. So g from 1 to the end. So in our case with d-dimensional data, this will actually be just g equaling 1. And we'll modify the gth component of this vector. So we'll increment it with eta multiplied by this difference, but now we'll have this element xij. Okay, so these formulas actually just correspond to the ones that we covered for regression. Yep, so remember, so as we discussed for SGD regression, we had these weight updates, w at step t+1 equals wt plus 1 plus 2 ether over L, and okay, we are throwing away this sum, and then we are left with the derivative yi minus w0 minus w1 xi. Okay, so this was for w0, and the same for w1, but with the okay, the same, but also xy here. Sorry, one moment. Okay, so we see pretty much the same formulas. So this is xij. The only difference here between derivatives with respect to w0 and all others is this multiplier xy. Yep, and for this was in 2 dimensions. So if we were to calculate w with respect to the derivative with respect to wj, so then we'll have xij here, so the gth component. Well, there's a slight difference that we threw away 1 over L here, so not much difference. So it's just a constant, and we also didn't calculate 2 here, so actually it doesn't differ. It's not actually that important. Just constants here. So suppose we just chose another eta, and then formulas will be different. So what is actually important here are these differences between the real yi and the prediction. Yep, so you see here w transposed multiplied by xi is actually the current prediction, our linear prediction here. So we see that our prediction is not ideal. This is the difference between the real value and prediction, and so we need to account for it. Okay, so some more about the code here. We need to be careful. Why did we actually need to have new W's here? So we see we first calculated, so we first made a copy of our weight vector W, and then we modified this copy, new W, and then we asserted, so we actually initialized W as this copy. We did it with the idea to carefully update these weights. So you see we've got W here, and if we are not careful enough, we'll update W0 at this step, and then our new update here will be not perfect. Yep, so suppose you update the original weight vector W at this point, and so here you'll be calculating the wrong formula. That's why we needed to make a copy of weight vector, and then we make updates with the values of W and assign the new values to the new vector, this new W. Okay, and so here we'll append this weight vector to our list weights with underscore, and we'll calculate mean squared error between vector y and our linear prediction. So we'll append this value to our list of MSEs. Okay, and we are also going to store the best value of W, this W with underscore. So we'll just take we'll take the best MSE at current point. So this argmin will return the index of the best value of MSE, and will return corresponding weights. Okay, and finally the fit method returns self. That means it returns the current instance of this SGDRegressor class. Our predict method is going to be really simple. So by the same token, we add the vector of ones to the left. And now our prediction is going to be linear, just x multiplied by this vector of the best values of W. Yep, so here at training, we saved this vector W underscore, so which provided the best value of our loss, minimal loss. So we've stored this vector W underscore, and we return our linear prediction. Okay, cool. So now I think it's really straightforward to understand what's going on here. I'll just add some more comments here. So we need this new W is used for simultaneous updates of V0 and so W0 and W1. And in general case, ... WD. So we need to update all of these simultaneously. Okay, and here we used special formula for simpler formula for the zeroth component for actually W0, and then a cycle over all remaining dimensions. Okay, so we are going to store the current weight vector and actually store current loss function. And here, W underscore will be actually the best vector of weights. So it provides the minimal value of our loss function. Okay, cool. Let's take a look how it's trained. So we've splitted our data, we also scaled it, and now we actually initialize our instance and feed it with our data. TQDM library provides this nice widget, so we can see that we've made one epoch, and then the second one, and then the third one. Now we're going to draw the values of loss function. So here we take this list of MSEs and just plot its values. So we've done more than 50,000 weight updates, and we see that MSE pretty quickly it's decreased up to almost 0. So we can see that maybe we didn't need all of these 3 epochs, so we did a nice job with only one epoch. So remember our dataset length is so initially 25,000, so then we took 70%, so it's about how many? Maybe 17,000 or so, so even one epoch will be nice here. So we can take a look at the best value of MSE. So it's 279, 71, and the corresponding values of our W vector, so W0, almost 68, and W1, so something close to 1. Just for fun, we can plot these weight updates, so separately for W0 and W1, how these were updated. And now we make a prediction for the validation set. So we've got a scaled validation set, we do a prediction and calculate MSE. Okay, 2.67. Now, just to check, let's do the very same thing with linear regression from sklearn. So we import it, we initialize it, feed with our scaled data, and print coefficients and calculate MSE on the validation set. So we've got pretty same coefficients. So this first one in the trained model, coef here will be just W1, and the intercept will be W0, so almost the same values as we had with our approach. And the final cell is the assertion. So we assume that the difference in MSEs between our SGD implementation and linear regression from sklearn, so we just think that it's less than 10 to the minus 4, and that's true. That's indeed the case. So we see we've got pretty much the same implementation, the same MSE and convergence to the same weights, W0 and W1, as in case of linear regression. So take a look at SGD classifier and regressor from sklearn. So if you just search for it, SGD classifier, sklearn, you can take a look at it. It will describe the very same process that we covered, but just take a look what arguments are there, what they stand for. You'll see that by default it trains a linear SVM. It turns out that in SGD fashion it's very simple to train actually an SVM. So I just leave it for you to dive into it. And in the next part we'll cover Voeppel-Webbit, and this idea of stochastic training will actually make it possible to train a simple model, this linear classifier with actually gigabytes of data, just in seconds or in dozens of seconds. Okay, so stay tuned. Good luck.